Hi everybody. I just wanted to talk a little bit about chapter 14. This kind of goes back to the material we talked about in chapter 4 on linear regression. And in that section we assume that there was no variation in the data. Remember that if you're taking a sample, then there could be some variation in the data. It may not represent the overall population, so that's what this chapter is about. And like I said, we're only going to cover section 14.1 on testing the significance of least squared regression models, and this will not be on the exam, but I did want you guys to do this section in terms of homework, just so you kind of get a feel for how things go. So what we're going to do is we're going to state the requirements of the least squared regression model, compute the standard error of the estimate, verify that the residuals are normally distributed, and conduct inference on the slope. And then lastly, construct a confidence interval about the slope of the least squared regression model. So let's take a look at objective 1. So objective 1 is to state the requirements of the least squared regression model. Requirement 1 for the inference on the least squared regression model is that for any particular value of the explanatory variable x, the mean of the corresponding response in the population depends linearly on x. That is, that the mean for some numbers beta sub 0 and beta sub 1, where yx represents the population mean response when the value of the explanatory variable is x. So the idea is, back in chapter 4 we assumed that we've had all the data, but now we're taking a sample, so again we don't really know whether the slope, so this would be the slope and the y-intercept, we don't know exactly what those are, and there's some variability or some probability in that those values might be off a little bit. So the response variables are normally distributed with a mean, again given by this formula, and a standard deviation of sigma. So in other words, when doing inference on least squared regression model, we require, first of all, that for any explanatory variable x, the mean of the response variable depends on the value of x through a linear equation, and that the response variable y is normally distributed with a constant standard deviation, in this case denoted by sigma, and the mean increase or decrease at a constant rate depending on the slope, while the standard deviation remains constant. So to kind of help you visualize this, right? So a large value of sigma, the population standard deviation indicates that the data are sort of widely dispersed. Remember, sigma is a measure of how dispersed the data is. So this would be your regression line here. But again, since we're dealing with a probabilistic model, right, it's possible that the regression line could really be off this line by a little bit, right? So the idea is this would sort of be the ideal line, but it could be off. And a small value of sigma indicates the data are fairly close to the actual regression line. So the least squared regression model then is given by the following equation here, where y sub I is the value of the response variable for the ith individual, beta sub 0 and beta sub 1 are the parameters to be estimated based on the sample data, and x sub I is the value of the explanatory variable for the ith individual, and epsilon I is a random error term with mean of 0 and a variance error. In this case, the variances, I guess, that kind of got messed up on this slide, are independent. And then again, I ranges over from 1 to the sample size, so the number of ordered pairs or data points in your set. So let's talk about how to compute the standard error of the estimate, which is S sub E is found using the formula, again given by this. So this goes back to chapter 4 where we were talking about residuals. So remember that the residuals then are the difference sort of between the regression line and the actual height of the data points. So let's look at an example of how to compute the standard error. So here we have some data about drilling, and again the length of time it takes to drill a certain number of feet. So we first of all need to look at the residuals, and we can use technology to find the least squared regression line. Again, this goes back to chapter 4. So the predicted values as well as the residuals for the 12 observations are given on the next slide. So these would be the predicted values, and then again the residuals again is the difference between the regression line and the actual height. So that square those differences and add them together. And then we find the sum of those residuals, again take the square root of that, and then divide by the number of samples minus 2, right? So that would give you the standard error of the estimate in this case, which would be 0.5197. So again, just be careful, make sure you divide by n minus 2. Then we need to compute the test statistic in this case, which would be a t statistic. Oh, and I guess we should also verify also before we do that that the residuals, again, these values over here, these would be the residuals, are normally distributed, right? And again, you can do that with a QQ plot. Again, I'm not going to expect you guys to compute that from scratch. So let's conduct inference on the slope. So we want to test whether the two quantitative variables are linear related. We use the following steps. The sample is obtained using a random sample. The residuals are normally distributed with a constant error variance. So these would be the hypothesis test then. So we want to basically determine whether beta sub 1 is equal to 0 or whether it's different from 0. Again, you'll be given your alpha level in this case. Compute the test statistic, which will be the difference in the y-intercepts divided by the standard deviation of the b sub 1 values. I'm sorry, this would be the slope, not the y-intercepts. And then use student's distribution with n minus 2 degrees of freedom. And so because we're assuming that beta sub 1 is equal to 0, right, then that will disappear. So we basically want to take the slope divided by the standard deviation of the slope. So using table 6 or some other method to compute the test statistic, that would give you the value. And then again, you'll have a two-tailed test, a left-tailed test, a right-tailed test. And again, you can, I guess, use the classical approach or the p-value approach, right? So if your computed statistic is less than the statistic you would look up on the table, depending on alpha, you will reject or accept the null hypothesis depending on what you have here. And then the p-value approach, again, you would just calculate the actual area. And then again, if the p-value is less than alpha, we reject the null hypothesis, just as in previous sections. So let's look at an example here, and then also don't forget to state the conclusion, obviously. So again, we should draw a residual plot to verify that the model is appropriate. But again, in most cases, you can assume that, or I'll give you the QQ plot. So let's look at a specific example here. So we'll do this at the 0.05 level of significance. So again, we have to, you should verify the requirements, but again, in most cases, you can assume that the requirements are met. So we assume that the experiment was randomized so that the data can be assumed to represent a random sample, obviously. We confirm that the residuals were normally distributed by constructing a normal probability plot already, and then we need to verify the requirement of constant error variance. So we plot the residuals against the explanatory variable for the drill depth here. And again, going back to chapter 4, right, there's no discernible pattern in the residuals. So again, these are not the original data points. These are the difference between the data points and the y coordinate. So step 1 then would be to determine again what our hypothesis is going to be in this case, right? So we'll have a two-tailed test, or in this case, the level of significance is 0.05. So use technology to calculate beta sub 1. and then determine the standard deviation of beta sub 1. We'll compute this. So again, all the calculations will be here on the next slide. So you'll calculate this, and then S sub B1 then will be the standard error of the estimate divided by the square root of the differences that we calculated earlier. Right? So that will give you 0.003. So plugging into the statistic here, right, we already calculated B sub 1. So plugging into the statistic we were talking about earlier, that would give you 3.867 for the calculated T sub 0 value. So then again, we can either use the classical approach. Again, since it's a two-tailed test, you'd want to divide alpha by 2. Again, look up the value with 10 degrees of freedom. So we'll get negative 2.228 and 2.228. Since the value of the test statistic is greater than 2.28, we'll reject the null hypothesis. Alternatively, using the classical, the p-value approach, again, we can actually find the actual area or an estimate of it. So finding the estimate of the area here, we see that the area or the probability underneath the curve is between these two values. In this case, the p-value is between, I'm sorry, these would be the t values here. So the probability value or the area then would be between 0.002 or 0.005, and so the p-value is less than our alpha level, so we would reject the null hypothesis. And then don't forget again to state the conclusion. So there is sufficient evidence that the alpha equals 0.05 level of significance to conclude that a linear relation does exist between drill depth and drill time. So that's one example there. Hopefully that'll give you an idea of what to do. I guess the one last thing we want to look at here is to construct a confidence interval, which would be, another way you could test the hypothesis, I guess, if you wanted to. But again, we're mainly emphasizing the classical and p-value approach. These would be your intervals for your lower bounds. So you can see this is basically what we just calculated, and then again you're adding or subtracting the same value here. So the one thing to note here is that the confidence interval formula for beta sub 1 can be computed only if the data are randomly obtained and the residuals are normally distributed and there is constant error variance. So as an example, let's construct a 95% confidence interval for the drilling data that we looked at earlier. So again, we calculated a lot of these things already. So B sub 1 is given by this, and S sub B sub 1, the standard deviation of the slope, is given by this. Remember, this is the slope of the line. So in this case, the value that we would get for the beta sub 1s, or the B sub 1s, are given by this, and then the calculated value we would add and subtract from that, right? So we're taking the B sub 1, this would be your value from the table, so that would be your T alpha over 2, and then this would be the number inside the square root, so you'll get a 0.0049 and 0.0183, so we could say that we're 95% confident that the mean increase in the time it takes to drill 5 feet for each additional foot of depth at which the drilling begins is between 0.005 and 0.018 minutes. Okay, so I hope that makes sense. I guess just to maybe talk a little bit more about the next section, although I didn't assign it. If you want to do it, you can. This next section is about confidence and prediction intervals. So again, if that's something you want to look at, I believe that is an optional homework assignment. So remember, the optional homework assignments, you'll be given extra credit for those. So again, I will be downloading all the grades into a spreadsheet at the end of the semester, and then I'll be taking out the extra credit sections and adding those into the homework, because I know right now they're not doing that. So anyway, so if you guys have questions or anything, just let me know.